Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all to the class of reanalysis. In today's lecture, we are going to discuss uh, an important property that is related to the supremum of a set. As you know, we are strictly focused on the book of Principle of Mathematical Analysis by Walter Rudin, and these properties are not available in this book. You can find these properties uh, in the book of R.G. Bartle. I am adding these properties in this playlist due to importance of your exam point of view. So I hope to follow this lecture. You are familiar with the concept of supremum, infimum, lower and upper bound, and bounded above and bounded below set. So let us start. Property number 3. In this property, the statement is, if S is a non-empty subset of R that is bounded above, and let A is any real number, define a new set A plus S is given by the A plus S that can be formed by adding A to the elements of set S. We have to show that supremum of the set A plus S is equal to A plus supremum of S. Firstly, we take a particular example and we show we check whether this property satisfied. For that example, suppose our set S is 1, 2, 3 up to so on 20. That is the set of first 20 natural number. Here supremum of this set S is equal to 20. As you know, supremum is a real number that is greater than or equal to every element of set S. So the supremum of this set S is 20. Let us we take A is equal to 3. Then here the new set, that is A plus S, that is here 3 plus S is equal to, is just by adding 3 to every element of set S. We have 3 plus 1, this will become 4, 3 plus 2, 5, 3 plus 3, 6, up to so on. Lastly, 20 plus 3, this is 23. Now, what is the supremum of this set? Supremum of 3 plus S. At this time, the supremum of 3 plus S 23. Now you can verify that the supremum of A plus S, that is supremum of 3 plus S, is equal to A plus supremum of S. What is A here? 3 plus supremum of S is 20. 3 plus 20 is equal to 23, which is equal to 3 plus supremum of S. So from this concrete example, we can see that this property is satisfied. Now we prove this property in general. Since it is given that your set S is non-empty, S is subset of R, and S is bounded above. As you know, a set is called bounded above if its upper bound exists. So S has an upper bound in R, an upper bound in R. Further, since R is complete, since R is complete ordered field, So by definition of complete ordered field, the supremum of the set S must exist and it belong to set of real number R. This implies, so supremum of S exists in R. Let supremum of S is a real number U. Say this is equation number 1. Now, by definition of supremum, we know that here U is the supremum of S. So, by definition of supremum, U is greater than or equal to every element of set S. So, U is greater than or equal to S, where S is an element of set S. To obtain the required form, we add A on both sides. So by adding A on both sides of the inequality, we have A plus U greater than or equal to A plus S. As A plus S is an arbitrary element of set A plus S. This shows that all the elements of this set A plus S are less than or equal to A plus U, or in other words, A plus U is greater than or equal to A plus S. This implies A plus U is an upper bound of set A plus S. So A plus U is an upper bound of A plus S. But according to requirement, we have to show that here, if we write supremum of S is equal to U, then this expression can be written as supremum of A plus S is equal to A plus U. What does this show? This shows that you are saying that A plus U is the least upper bound of A plus S. This expression shows that A plus U is the least upper bound of A plus S. Supremum means least upper bound. Least upper bound of A plus S is equal to A plus U. It means A plus U is the least upper bound of A plus S. So our target is to show that A plus U is the least upper bound of A plus S. We need to show that we need to show that A plus U is least upper bound of set A plus S. For this, we suppose there is an other upper bound V of this set A plus S, which is greater than this upper bound A plus U. For this, we choose an other upper bound of A plus S, and we show that V is greater than or equal to A plus U. When V is greater than or equal to A plus U and V is also an upper bound, this will show that A plus U is the least upper bound. So now our target is to show this inequality. So as here we are taking V as an upper bound, for this we choose an other upper bound V. As we are taking V as an upper bound of A plus S, so by definition of upper bound, V is greater than or equal to every element of set A plus S. So by definition, this implies V is greater than or equal to every element of set A plus S. As the set A plus S has elements of the form a plus small s, it means v is greater than or equal to a plus s. By subtracting a on both sides, we have v minus a is greater than or equal to small s. Now, what does this inequality shows? As s is arbitrary element of set s, and here v minus a is greater than or equal to this element s, this implies v minus a is an upper bound of set S. As we know that upper bound is always greater than or equal to least upper bound. This implies upper bound of S is greater than or equal to least upper bound of S. Now, what was the least upper bound of set S? Least upper bound of S means supremum of S. So, what was the least upper bound or supremum of S? We have assumed that the supremum of S is U. Supremum of S is U. It means upper bound of S, that is now V minus A. This implies V minus A is greater than or equal to supremum of set S, implies V minus A is greater than or equal to U. This shows that by adding A on both sides, V is greater than or equal to A plus U. That was our target to show. We need to show that this inequality V is greater than or equal to A plus U, and from this inequality we leads to A plus U is the least upper bound, because both are the upper bound of set A plus S. Now V is greater than or equal to A plus U shows that V is another upper bound which is greater than or equal to A plus U. This implies A plus U is the least upper bound of set A plus S. In other words, you can say that supremum of A plus S is equal to A plus U. As U is supremum of S, this implies by substituting U is equal to supremum of S, we obtain the required result. So this is a simple proof. I hope after this lecture you have a clear understanding of this proof. Inshallah, in the next lecture we will discuss another property that is similar to this property. That is actually we need to show that infimum of A plus S is equal to A plus infimum of S. So we will discuss this property in the next lecture. Until then, take care. Allah Hafiz.